A single point of light travels for 13.4 billion years. It should not exist. When we capture this light, we are looking back in time. We see a galaxy as it was just under 300 million years after the Big Bang. The universe then was an infant, only 2% of its current age. In that primordial era, only the simplest elements were present. Hydrogen and helium were the only building blocks available. Yet this distant galaxy is ablaze with the signature of oxygen. Oxygen is a complex element. It demands the lives and violent deaths of entire generations of stars to come into being. This single impossible discovery forces us to tear up the first chapter of cosmic history. We are about to witness chemistry that defies the known timeline of the universe. We will explore what this means for everything we thought we knew. The story begins with a discovery that shatters our most fundamental rules. A galaxy was found existing in an epoch when the cosmos was barely cooling. Imagine compressing the entire 14 billion year history of the universe into a single calendar year. This galaxy appears fully formed on January 7th. Everything we understand about physics, about how stars are born and how elements are made, tells us this is impossible. The discovery was made in a tiny, unassuming patch of the sky in the constellation Fornax. When the James Webb Space Telescope focused its golden eye on this region, astronomers were searching for the first, most primitive cosmic structures. They expected to find faint, disorganized clumps of gas. Instead, they found a system burning with a chemical sophistication that should have taken billions of years to develop. Its official designation is a long string of letters and numbers. To the scientists who found it, it is simply the record holder. It sits at a distance that translates to a look-back time of 13.4 billion years. Here is the heart of the paradox. At 300 million years after the universe's birth, the cosmos was in its absolute infancy. The situation is more jarring than seeing a newborn baby solving calculus. This galaxy is rich with oxygen. That one fact is a cosmic crime. Oxygen requires multiple generations of massive stars to be forged, and each generation takes millions of years to live and die. The timeline simply does not add up. Our established models of cosmology predict that galaxies from this era should be small and dim. They should be chemically simple, made of little more than hydrogen and helium. This galaxy violates every single one of those predictions. It shines with a brightness that makes astrophysicists deeply uncomfortable, exceeding expectations by a staggering amount. It is not a compact knot of gas. It stretches across 1,600 light-years, a substantial size for such a young object. And most shocking of all, Webb's instruments detected a strong, undeniable signal of oxygen mixed throughout its stars and gas. The element oxygen can only be created deep inside the nuclear furnaces of massive stars. Those stars must then live out their lives and explode as supernovae. These cataclysmic explosions are the only way to scatter the newly forged elements into the surrounding space. From that enriched dust and gas, a new generation of stars can form. This is the cycle of cosmic enrichment, and it cannot be rushed. Physics itself places a speed limit on how fast stars can evolve. The research teams worked backward, calculating from the amount of oxygen they observed. Their models showed that the galaxy must have been furiously forming stars for at least 100 million years before the moment we are seeing it. This pushes the dawn of star formation back to within 200 million years of the Big Bang itself. At that time, the universe had barely cooled enough from the initial fireball for atoms to even exist. Dense clouds of gas had hardly begun to collapse under the slow, patient pull of gravity. Yet somehow this system pulled itself together. It ignited not one but multiple generations of stars, and it cooked up complex chemistry at a pace our theories cannot fathom. Two independent teams of scientists verified the discovery. They used different instruments on the James Webb Telescope to be certain. The Near-Infrared Camera, or NIRCam, captured the first images of the faint red smudge. The mid-infrared instrument MIRI is what revealed the shocking spectral signature of oxygen. Later observations from a telescope on Earth confirmed it all. The Atacama Large Millimeter Array in Chile, a vast collection of radio dishes, detected the same oxygen signal with incredible precision. The measurements from space and the ground from infrared to radio wavelengths all aligned perfectly. What we are looking at is a fundamental challenge to cosmology. Time is the antagonist of this story. The universe has strict rules about how quickly things can evolve. Stars require millions of years to coalesce from gas. They need millions more to burn through their nuclear fuel, and they need to reach the end of their lives to die and spread their elemental ashes. This galaxy appears to have completed this entire cosmic marathon in less time than it takes to run the first lap. Think of it like baking a loaf of sourdough bread. Mixing the ingredients is fast, but the dough needs hours to rise, a slow and patient process of chemistry. Then it needs more time in a hot oven to become bread. You cannot shortcut these steps. The chemistry demands its own schedule. Stellar alchemy, the process of creating new elements, operates under the same rigid constraints. Hydrogen fuses into helium over millions of years in the core of a star. As the star ages heavier, elements are built up in sequential stages of burning. The final explosion that distributes these elements only happens after the star has exhausted every last drop of fuel. The numbers for this galaxy create an equation with no solution. It appeared 290 million years after the Big Bang. The oxygen in its spectrum is present in quantities that match galaxies billions of years older. The very first stars in the universe needed time to collapse from the primordial clouds of gas. Our best estimates place the formation of these first stars no earlier than 100 to 200 million years after the beginning. This leaves a window of at most 150 million years. Within that impossibly short time, a whole sequence of events had to occur. The first generation of stars had to form from pure hydrogen and helium. These were the population 3 stars, theoretical giants, that were likely 30 to 300 times more massive than our Sunday. These titans would have burned incredibly hot and bright. They would have exhausted their fuel in just a few million years. When they exploded, they would have dispersed the first batches of oxygen, carbon, and other heavy elements into the gas around them. That newly enriched gas would then have to cool and collapse all over again. A second generation of stars would then form from this enriched material. Some of these stars, if massive enough, would also burn through their fuel and explode. The cycle would have to repeat again and again. Each iteration adds more heavy elements to the cosmic soup, building the concentration over time. To reach the oxygen levels seen in this galaxy, multiple cycles are needed. Each one of those cycles is a multi-million-year process. Our most advanced computer simulations of the early universe consistently show that building up a significant amount of metals, the astronomical term for any element heavier than helium, takes far longer than this galaxy had. The models account for factors like how quickly gas can cool, the time it takes for gravity to collapse a cloud, and the known phases of stellar evolution. Even when scientists push every single assumption in their models to the absolute physical limit, they cannot make the timeline work with conventional physics. Some have proposed that early stars formed much faster than we predict. Others suggest that supernovae were much more efficient at distributing their contents in the denser environment of the early universe. A few radical theories even propose that the first stars were far more massive than we believe, allowing them to burn and die on accelerated timescales. None of these explanations feels complete. Each one requires rewriting a fundamental piece of our understanding of how gravity, pressure, and nuclear fusion work. The timeline problem is not isolated to this single galaxy. The James Webb Telescope has found other systems at similar distances that show a similar shocking level of maturity. The pattern suggests this is not a statistical fluke but a systematic feature of the early cosmos. The universe, it seems, figured out how to build complex galaxies much faster than our theories ever predicted. How it achieved this remains a terrifyingly open question. Let's rewind to the absolute beginning. Before anything, there was nothing. Then everything exploded into existence. In the first few seconds after the Big Bang, the universe was an unimaginably hot and dense plasma. Temperatures soared into the billions of degrees, too hot for even atoms to form. Matter was a seething soup of fundamental particles like quarks and gluons colliding in pure chaos. As the universe expanded, it began to cool. Within about 3 minutes, protons and neutrons could bind together. The first atomic nuclei were forged in this era, an event known as Big Bang nucleosynthesis. This process created the universe's initial inventory of light elements. Hydrogen nuclei, which are just single protons, appeared first. Some of these collided and fused to form deuterium, a heavier form of hydrogen with 1 proton and 1 neutron. Deuterium nuclei then fused to create helium, with its 2 protons and 2 neutrons locked together. The process continued for a brief time, creating trace amounts of lithium. Then the expansion cooled everything below the temperatures needed for fusion. The nuclear reactions ceased. The universe was left with a composition of roughly 75% hydrogen and 25% helium by mass. Lithium was a mere trace element, less than 1 part in 10 billion. Nothing heavier than lithium existed anywhere in the cosmos. This primordial soup of nuclei drifted in darkness. Even though nuclei had formed, complete atoms could not exist yet. The universe was still too hot. Free electrons zipped around, unable to settle into stable orbits around the nuclei. Photons, the particles of light, were constantly scattering off these free electrons. This made the cosmos opaque, like a thick, dense fog where light could not travel more than a few feet. 380,000 years had to pass. Only then did the universe cool enough for electrons to finally bind with nuclei. Neutral atoms could at last form. A hydrogen atom appeared, a single electron orbiting a single proton. A helium atom formed with 2 electrons orbiting its nucleus. This moment, known as recombination, is when the fog finally cleared. Photons were now free to travel unimpeded through space. The cosmic microwave background radiation that we can still detect today began its long journey at that exact instant. Now, the universe was transparent, but it was also profoundly dark. Atoms existed, but no stars had yet ignited. No galaxies had yet formed. Space was filled with vast, invisible clouds of hydrogen and helium gas, slowly drifting under the gentle persuasion of gravity. Tiny variations in density, the echoes of quantum fluctuations from the Big Bang itself, created regions that were slightly denser than their surroundings. These denser patches had a slightly stronger gravitational pull. They began to draw in more gas from the space around them. The cosmic dark ages had begun. For the next 200 million years, very little happened. No stars shone. No nuclear fusion occurred anywhere. The universe was cold, dark, and in a state of quiet anticipation. The clouds of gas continued to grow denser as gravity patiently did its work. Slowly, gradually, some of these clouds compressed to the point that their centers began to grow hot. Pressure mounted and the temperature climbed. Finally, in the very densest cores of these clouds, hydrogen nuclei began to collide with enough force to fuse together. The first stars ignited. They blazed into existence, made of pure hydrogen and helium. Nothing else was available. No carbon existed to form planets. No oxygen existed to create water. No iron existed to build rocky cores. The universe contained only the 2 lightest elements from the periodic table. Everything heavier had to be manufactured inside the hearts of these new stars. The periodic table was mostly empty, waiting for stellar alchemy to fill in the blanks. That pristine chemical simplicity is what makes the discovered galaxy so profoundly baffling. Where on Earth, or rather where in the universe, did its oxygen come from? Imagine a universe filled with light, but with nothing to see. After the event of recombination released the cosmic microwave background, photons streamed freely through space, yet there was nothing to reflect or absorb them in any interesting way. There were just endless expanses of transparent, featureless hydrogen and helium gas. No stars, no galaxies, no structure of any kind would have been visible to a hypothetical observer. This dark age lasted for perhaps 200 million years, maybe as long as 400 million. The exact duration is one of the great unknowns because we have not yet directly observed the very first stars. They lie just beyond the detection limits of our current telescopes, a tantalizing prize just out of reach, even for an instrument as powerful as James Webb. We know they must have existed because later galaxies like our record holder show their chemical fingerprints. The darkness had to end. During these long, dark millennia, gravity was the universe's tireless sculptor. Invisible dark matter had already begun to cluster into vast, unseen halos. Its powerful gravity pulled the normal matter along for the ride. Streams of hydrogen and helium gas flowed toward the densest concentrations of dark matter. The gas clouds grew larger and more massive. Eventually, some of them reached a critical threshold. The sheer pressure from their own immense weight began to heat their cores. Picture watching a cosmic collapse in extreme slow motion. A cloud of gas spanning dozens of light years begins to contract. Over millions of years it shrinks. The center compresses and the temperature rises from the incredible pressure. All of this happens in absolute silent darkness. No light signals this grand transformation. The universe remains pitch black. Only the force of gravity reveals that anything is changing through its inexorable pull on the surrounding matter. When the temperatures in the cores hit several million degrees, nuclear fusion ignites. Hydrogen fuses into helium, releasing a tremendous amount of energy. Photons stream outward from the core. Light appears in the universe for the first time in eons. A star is born. This solitary point of light is what finally broke the darkness. For the first time since recombination, a fusion-powered beacon began to shine. The Dark Ages started to come to an end. These pioneer stars were radically different from the stars we see in the sky today. Lacking any heavy elements which act as cooling agents, the gas clouds could not easily fragment into smaller pieces. Stars forming from pure hydrogen and helium therefore tended to be enormous. Many of them were likely more than 100 times the mass of our own Sunday. Some may have even reached 300 times that benchmark. Such giants would have burned incredibly hot. Their surfaces would have glowed with a brilliant blue-white light, with temperatures exceeding 100,000 degrees. They would have shone with the brightness of millions of ordinary stars combined. Their lifetimes would have been tragically brief by stellar standards, perhaps just a few million years from birth to a violent death. In that short span, they would have utterly transformed the universe around them. The intense ultraviolet radiation from these first stars began to ionize the surrounding hydrogen gas. Neutral atoms absorbed the energetic photons, and their electrons were stripped away from their nuclei. Bubbles of ionized plasma began to form around each new star, expanding out into the neutral gas. As more and more stars formed, more of these bubbles appeared. Eventually, the bubbles began to merge. Vast regions of the universe became ionized. This process, called reionization, gradually transformed the entire cosmos from neutral back to ionized over the course of perhaps 500 million years. The epoch of reionization marks the transition from the Dark Ages to a universe filled with light and complex structure. Galaxies began to form in earnest. Stars clustered together under their mutual gravity. The modern universe started to take the shape we recognize today. The discovered galaxy exists right on the boundary between the darkness and the light. It formed when reionization was just getting underway. It somehow managed to assemble itself during the final twilight stages of the Dark Ages. That critical timing makes its chemical sophistication even more of a puzzle. There was barely enough time for even a single generation of stars, let alone the multiple generations required for its oxygen content. The presence of oxygen tells a story of incredible violence. This element cannot be formed in the Big Bang. It cannot be formed in small stars like our Sun. It requires the extreme temperatures and pressures found only in the most massive stars during their final desperate moments. Finding oxygen in this very early galaxy means finding the evidence of stellar death, specifically supernova explosions repeated multiple times. Every single oxygen atom in that galaxy began its existence inside the core of a star. Nuclear fusion built it up through a sequence of careful reactions. First, helium nuclei fuse to create carbon. This requires 3 helium nuclei to collide almost simultaneously, overcoming their enormous repulsive forces to bind together. This reaction produces a carbon-12 nucleus with 6 protons and 6 neutrons. The process is only possible because of an extraordinary coincidence in the energy levels of the nuclei that makes carbon formation feasible. Once carbon exists, adding another helium nucleus creates an oxygen-16 nucleus. This has 8 protons and 8 neutrons. This reaction releases a burst of energy which helps to power the star against its own gravity. As fusion continues, layers of carbon and oxygen accumulate in the stellar core. Heavier elements form in concentric shells around them. The star develops an onion-like structure, with different elements being forged at different depths. This process of element building only happens in stars that are massive enough to compress their cores to the required temperatures and densities. Smaller stars like our Sun cannot achieve the necessary conditions. They will stop their fusion process at carbon and oxygen, which will then remain locked forever inside their white dwarf remnants. Only stars above roughly 8 times the mass of our Sun can proceed further up the periodic table. They fuse oxygen into neon and magnesium. They fuse neon into still heavier elements. Each stage of fusion requires higher and higher temperatures and lasts for a shorter period of time. The final stages of burning happen with breathtaking speed. Silicon fuses into iron and other iron peak elements in just a matter of days. Iron begins to accumulate in the very center of the core. Then disaster strikes. Iron is the ultimate stellar ash. It cannot be fused to release energy. In fact, fusing iron consumes energy instead. The core suddenly loses its pressure support, and gravity wins a decisive victory. The core collapses in less than a single second. Material from the outer layers of the star falls inward at velocities approaching 1/4 of the speed of light. The collapse only halts when the core is crushed to the density of a neutron star. The infalling material then rebounds off this incredibly hard, incompressible surface. A powerful shockwave forms which begins to race back outward through the star. This shockwave initially stalls, unable to overcome the immense pressure of the still infalling material. But a torrent of neutrinos, ghostly particles streaming from the collapsed core deposits energy into the stalled shock. The shock is revived. It plows through the outer layers of the star, and the temperature spikes. The elements in those outer layers undergo a final explosive round of fusion reactions. As the shock wave passes through, the entire star explodes. A core collapse supernova unleashes more energy in a few seconds than the star emitted during its entire previous lifetime. The explosion tears the star to pieces. All the oxygen, carbon, neon, magnesium, silicon, and iron that were produced during the star's life are hurled into space at thousands of miles per second. These heavy elements are dispersed across dozens of light years of space. This ejected material then mixes with the surrounding interstellar gas. Clouds of gas enriched with oxygen and other heavy elements begin to drift through the galaxy. When these enriched clouds eventually collapse to form new stars, those second-generation stars inherit the chemical legacy of their predecessors. The planets that form from the leftover disk of material also contain these heavy elements. This is how chemical complexity enters the universe. The oxygen detected in that distant record-breaking galaxy proves that this entire violent cycle happened multiple times within the first 300 million years. Multiple generations of massive stars had to form live fuse elements and then explode. The explosions had to disperse their oxygen into the surrounding gas. That gas then had to cool and form more stars, which continued the process of enrichment. The cycle had to repeat enough times to build up 10 times more oxygen than our models predict should exist at that early epoch. The glowing line of oxygen in the galaxy's spectrum is a signature of both death and rebirth. Stars are the factories that create the elements, but supernovae are the delivery trucks that distribute them. Without these catastrophic explosions, all the carbon, oxygen, and heavier elements forged in stellar cores would remain locked inside their stellar remnants forever. Supernovae are the essential delivery mechanism that makes chemical evolution possible across the entire universe. The process of the explosion itself creates additional elements beyond what was formed during the star's stable lifetime. As the shock wave plows through the outer layers of the star, it heats the material to billions of degrees. At these extreme temperatures, atomic nuclei collide with enormous energy. Rapid fusion reactions create elements that the star never produced during its normal stable burning phases. Elements like calcium, titanium, and more iron peak elements are formed in significant quantities during these explosive final seconds. Consider the sheer energy involved. A single core collapse supernova releases approximately 10 to the power of 51 ergs of energy. This number is almost beyond human comprehension. It is more energy than the star emitted as light during its entire 10 million year lifetime. It is more energy than an entire galaxy of 100 billion stars emits in several seconds. Most of that energy escapes in the form of neutrinos, those ghostly particles that barely interact with matter. But even the tiny fraction of energy that is converted into the kinetic energy of the explosion is enough to tear the star apart. The expanding debris travels outward at velocities between 5,000 and 20,000 kilometers per second. Nothing can stop this material. It plows into the surrounding gas, creating a shock wave that sweeps up even more material as it expands. The supernova remnant continues to expand for thousands of years, eventually merging with the general interstellar medium of the galaxy. The heavy elements become thoroughly mixed throughout the galactic gas, available for incorporation into future generations of stars and planets. Early in cosmic history, these explosions would have had a disproportionately large impact. The universe was much denser back then. Galaxies were much smaller. A single supernova explosion could have enriched a significant fraction of a dwarf galaxy's entire gas supply. The very first supernovae essentially polluted their entire host systems with heavy elements. This pollution, however, was essential for enabling the formation of smaller, longer-lived stars and eventually planets capable of supporting life. The rate of supernova explosions in the early universe remains an uncertain number. The first generation of stars formed purely from hydrogen and helium were likely very massive. Most of them would have ended their lives as supernovae. If star formation began around 200 million years after the Big Bang, and these massive stars only live for a few million years, then supernovae could have started occurring by 205 million years. This leaves a potential window of 85 million years for multiple generations of enrichment before we observe the galaxy in its current snapshot. The models that attempt to reproduce the observed oxygen abundance struggle with the issue of efficiency. How many stars must form and explode to create the detected levels of oxygen? How efficiently does the ejected material from these explosions mix with the surrounding gas? How quickly can that enriched gas cool down enough to collapse and form a new generation of stars? Each one of these questions introduces new uncertainties into the calculation. Multiplying these uncertainties together creates large error bars in the final prediction. Even when pushing every single assumption to maximize the efficiency of early enrichment, the models can barely match the observations. Some researchers have proposed that the initial mass function in the early universe, which is the distribution of stellar masses, was heavily weighted toward massive stars. If nearly all of the first-generation stars were massive, then nearly all of them would explode as supernovae, which would maximize the production of heavy elements. However, this creates other problems. Massive stars are less efficient at forming and require a significant amount of gas. Forming enough of these massive stars quickly enough challenges our understanding of the physics of star formation. The supernova requirement creates a fundamental minimum timescale problem. You need time for stars to form. You need time for them to evolve and die. You need time for their ejected material to disperse and mix with the surrounding gas. You need time for new stars to form from that enriched gas. Every single step in this process takes millions of years. The sum total of these steps should easily exceed 100 million years. This galaxy appears to exist before that timeline could have reasonably completed even once, let alone multiple times. The heavens reveal their ancient violence through the soft glow of oxygen. The discovery of this galaxy required looking at the universe in wavelengths of light that are invisible to human eyes. The James Webb Space Telescope observes primarily in the infrared part of the spectrum, detecting heat rather than visible light. This unique capability makes it perfectly suited for finding the most distant objects in the universe. The light from these remote galaxies gets stretched by the expansion of the cosmos. Light that was originally emitted as visible or even ultraviolet light arrives at our telescopes redshifted into infrared wavelengths. The James Webb Telescope is designed to capture this ancient stretched light. The near-infrared camera was the primary instrument used for the initial detection. This camera, built under the direction of the University of Arizona, can detect light with wavelengths from 0.6 to 5 microns. For comparison, visible light spans from about 0.4 to 0.7 microns. The camera can see just beyond the red end of human vision into the near-infrared. It achieves this incredible sensitivity by cooling its detectors to -388 degrees Fahrenheit, just 33 degrees above absolute zero. At these frigid temperatures, the thermal noise in the detectors decreases enough that incredibly faint signals become detectable. The telescope was pointed at a region of the sky known as the Jades fields. Multiple teams have observed these fields repeatedly over the years, building up incredibly deep images through very long exposures. The galaxy appeared as a tiny, faint red dot. Its color was an immediate signal of a very high redshift. The blue and green wavelengths were completely absent from its light, indicating that those wavelengths had been stretched so far that they were beyond the detection limits of the telescope. Only the very reddest channels of the camera showed any signal at all. Spectroscopy was what confirmed the incredible distance. Rather than just taking a picture, the instruments on Webb can disperse the light from an object into a spectrum, spreading the different wavelengths out across a detector like a rainbow. This spectrum revealed a characteristic pattern known as the Lyman break. Hydrogen atoms absorb ultraviolet light at very specific wavelengths. In the galaxy's own reference frame, this absorption occurs at 121.6 nanometers. That light was emitted 13.5 billion years ago when the universe was just 2% of its current age. The expansion of the cosmos stretched that wavelength by a factor of 15.3. It arrived at our telescope at 1.8 microns firmly in the infrared. But the real jaw-dropping surprise came from the mid-infrared instrument, or MIRI. This instrument observes even longer wavelengths of light from 5 to 28 microns. At these specific wavelengths, certain emission lines from the element oxygen become detectable. Oxygen ions emit light at particular wavelengths when they are excited. For this incredibly distant galaxy, those emission lines should have been redshifted into Miri's detection range if any oxygen was present. Miri detected the oxygen line. The signal appeared at 7.7 microns, stretched from its original rest wavelength of 0.501 microns by that same redshift factor of 15.3. The line was bright, indicating a significant abundance of oxygen. This was not a marginal detection that required complex statistical arguments. The signature of oxygen blazed clearly in the data. The observations required an extraordinary amount of dedication from the science team. They spent 167 hours imaging the field with the near-infrared camera. They spent another 43 hours imaging with Miri. This totals over 200 hours of precious telescope time, all focused on a region of the sky smaller than a single grain of sand held at arm's length. Such a massive commitment of time reflects the immense importance of the target. Only the most distant and scientifically interesting objects warrant this level of investment. Luck also played a crucial role in the discovery. The galaxy just happened to sit in a position that was perfectly aligned with the fields of view of both instruments. If the telescope had been pointed just a fraction of a degree differently, Miri would have missed the target entirely. The team would never have detected the oxygen, and the discovery might have been delayed for years, waiting for future observations. Serendipity combined with skill to capture this incredible snapshot of the infant universe. The infrared detection capability of the James Webb Telescope, which was impossible just a few decades ago, has opened a new window on the era of cosmic dawn. Older telescopes like the Hubble Space Telescope, which operate primarily in visible wavelengths, simply cannot see these ancient galaxies. Their light has been shifted too far into the red. Webb's design specifically targets this cosmological regime, allowing us to witness the universe in its first few 100 million years for the very first time. What we are seeing there directly contradicts what we expected to find. The new technology is revealing some uncomfortable truths. The galaxy shines far too brightly. Objects at such extreme distances should appear incredibly faint, barely detectable, even with our most powerful instruments. This one blazes with an unexpected intensity. Its brightness exceeds the theoretical predictions by factors that cannot be easily explained. Something about the early universe was capable of producing exceptionally luminous systems. Luminosity is fundamentally dependent on the total mass of the stars in a galaxy. Massive stars shine much brighter than small stars. A star that is 100 times more massive than our Sun shines roughly 1 million times brighter. The brightness scales dramatically with mass. If this distant galaxy contains a population of predominantly massive stars that could potentially explain its brightness, but forming a population of only massive stars requires special conditions that may not have existed universally. The efficiency of star formation also matters. How much of a galaxy's available gas mass is converted into stars determines the total light output. If star formation proceeded with exceptional efficiency in this galaxy, packing more stellar mass into a compact region, the system would naturally shine brighter. However, our current models of early galaxy formation actually predict a low efficiency. The gas in the early universe should have been difficult to cool and collapse efficiently, leading to slow and inefficient star formation. The observations directly contradict this prediction. Another possibility involves the contribution from an active galactic nucleus. Perhaps a supermassive black hole already existed at the center of this galaxy, accreting material and releasing enormous amounts of energy. The process of black hole accretion can easily outshine the entire stellar population of a galaxy. However, explaining how a supermassive black hole could have formed so early in the universe creates a different, equally challenging problem. These massive objects typically require hundreds of millions of years to grow. to substantial masses, either through the accretion of gas or the merger of smaller black holes. The specific luminosity value of this galaxy is what raises so many eyebrows. The galaxy appears to be roughly as bright as other galaxies that are 10 times more massive. Either it contains far more stars than its compact size would suggest, or the stars it contains are intrinsically much more luminous than typical stars. Neither of these explanations fits comfortably within our standard models. The first requires packing an implausible amount of stellar mass into a very small volume. The second requires assuming the existence of unusual stellar populations that should not dominate so completely. Comparisons with nearby galaxies help to illustrate the paradox. Modern star-forming galaxies that have similar stellar masses show a predictable range of brightness. This ancient system dramatically exceeds those expectations. It is behaving like a galaxy that has had billions of years to form its stars, not just a few hundred million. The compression of evolutionary timescales appears in multiple properties of this object, not just its chemical composition. It is possible that dust extinction could be hiding some of the true brightness. Dust in galaxies absorbs ultraviolet and visible light, and then re-emits that energy as infrared light. This process shifts the energy to longer wavelengths. However, dust itself is composed of heavy elements, primarily carbon and silicon. The early universe lacked a sufficient quantity of heavy elements to produce a significant amount of dust. This galaxy's high oxygen abundance suggests that some dust might exist, but probably not enough to dramatically affect the observations. The brightness appears to be intrinsic to the galaxy itself. Multiple studies have verified the luminosity measurements using different methods. Photometry in various infrared bands consistently shows the same high level of brightness. Spectroscopic measurements have confirmed the distance, ruling out any possibility of contamination from foreground objects. The galaxy really is that bright, and it really is at that distance. The measurement is solid, but the physics behind it is puzzling. Some theorists have suggested that star formation in the early universe may have proceeded in short, intense bursts, rather than in a steady, continuous manner. Perhaps we caught this galaxy during an exceptional burst of star formation, which is temporarily making it far brighter than average. If we were to observe 100 similar galaxies at this distance, most of them might appear much fainter, with only a few caught during these peaks of brightness. However, the limited statistics that are available so far do not seem to support this interpretation. The few distant galaxies that have been found all show similarly unexpected properties. The luminosity paradox extends beyond this single object. The James Webb Telescope has found multiple galaxies at similar distances that show an elevated level of brightness. The pattern suggests that something systematic about early galaxy formation was different from our current expectations. Perhaps the initial conditions, the nature of the dark matter halos, or the physics of gas cooling worked differently at those very early times. Understanding these differences will require new theoretical frameworks and many more observations. The brightness of a galaxy provides a window into its stellar population. Distance in the field of cosmology is a complicated concept. The light from remote objects has traveled for billions of years to reach our telescopes. During that long journey, space itself has been expanding, stretching the wavelength of the light. The amount of this stretching, which is called redshift, is what tells us the distance to the object. This particular galaxy has a redshift of 14.3, placing it among the most distant objects ever observed. Redshift works through the Doppler effect combined with the expansion of the cosmos. As space expands, it carries galaxies apart from one another. Light traveling through this expanding space gets stretched to longer, redder wavelengths. Redder wavelengths mean lower energy. The more that space has expanded during the light's journey, the more stretched the light becomes. We measure this stretching by comparing the observed wavelengths of features in the galaxy's spectrum to the known wavelengths at which those features are emitted. For this galaxy, every single wavelength of its light has been stretched by a factor of 15.3. This number comes from 1 plus the redshift value. Ultraviolet light that was emitted at 100 nanometers arrives at our telescope as infrared light at 1,530 nanometers. Visible light is shifted so far into the red that it is beyond detection. Only light that was originally emitted as visible or ultraviolet remains detectable at all after this extreme amount of stretching. Converting a redshift value to a distance requires a specific cosmological model. We must assume values for the universe's expansion rate, its matter density, and its dark energy density. Using the current best measurements, which give a Hubble constant of 67 kilometers per second per megaparsec, a redshift of 14.3 corresponds to a light travel time of 13.4 billion years. The light from this galaxy left on its journey just 290 million years after the Big Bang. However, the galaxy itself is now much farther away than 13.4 billion light-years. While the light was traveling toward us, the universe continued to expand, carrying the galaxy even farther away. The current proper distance to this galaxy's location is approximately 46 billion light-years. We can never visit this location. It is receding from us faster than the speed of light due to the expansion of space itself. This extreme redshift places the object firmly in the epoch of reionization. This was the time when the universe was transitioning from being mostly neutral to being mostly ionized. During this era, the very first galaxies were just beginning to form. Structure was just starting to emerge from the nearly smooth primordial density field. Observing objects at these incredible distances means that we are witnessing cosmic dawn directly. We are seeing the universe in its absolute infancy. Measuring such high redshifts requires spectroscopy, not just photometry. Taking a picture of an object can show that it appears red, but it cannot precisely determine how red it is. Spectroscopy spreads the light out into its component wavelengths, revealing specific features like emission and absorption lines. These features have known rest wavelengths that have been determined from laboratory measurements. The observed wavelengths of these features are then divided by their rest wavelengths to calculate the redshift factor. For this galaxy, multiple spectral features all confirm the same redshift value. The Lyman break appears at the expected wavelength. The oxygen emission lines appear at wavelengths that are consistent with that same redshift. Hydrogen emission features also align perfectly. All the pieces of the puzzle fit together, leaving no doubt about the galaxy's distance. Independent measurements by different instruments all agree. The redshift is secure. Higher redshifts push us ever closer to the theoretical limit of what can be observed. At a redshift of around 30, we would be approaching the epoch when the very first stars are thought to have formed. Beyond that lies the cosmic dark ages, when no stars had yet shone. Currently, a redshift of 14.3 represents the very edge of our detection capabilities. A few candidates at redshifts of 16 or 17 have been reported, but they still require confirmation. This galaxy remains among the most distant confirmed objects ever found. Every increase in the observable redshift reveals earlier and earlier cosmic conditions. At a redshift of 1, we are seeing galaxies as they were 7.7 billion years ago. At a redshift of 6, we see galaxies from the first billion years of the universe. At a redshift of 14, we see galaxies from the first 300 million years. Each of these steps into the past requires exponentially more powerful instruments. The James Webb Telescope reaches farther back in time than any previous telescope, but even it cannot see all the way back to the very first stars. That will require the next generation of instruments. The redshift number encodes vast expanses of both space and time. 14.3 means we are looking back across more than 97% of cosmic history. It means we are seeing light that began its journey when the universe was 40 times younger than it is today. It means we are witnessing an era when galaxies were just learning how to exist. The number is more than just a measurement. It is a reading from a time machine. The term metal abundance in astronomy has a very specific meaning. Any element that is heavier than helium is counted as a metal. This includes carbon, oxygen, neon, magnesium, silicon, sulfur, and iron. The term might sound strange to a chemist, but astronomers use it consistently. This distant galaxy contains metals at levels that are 10 times higher than our models predict should exist at its early epoch. This measurement comes from the strength of the spectral lines. Oxygen ions emit light at specific wavelengths when their electrons transition between different energy levels. The brightness of these emission lines relative to the brightness of hydrogen lines indicates the ratio of oxygen to hydrogen atoms. For this galaxy, that ratio exceeds 1 part in 10,000 by the number of oxygen atoms. This might sound like a tiny amount, but it represents a substantial level of enrichment compared to the primordial composition of the universe, which contained essentially 0 heavy elements. The composition of our own sun provides a useful reference point. The material in and around our local star contains roughly 1 part in 500 oxygen atoms compared to hydrogen. This represents the accumulated enrichment from 9 billion years of stellar generations in the disk of the Milky Way galaxy. The newly discovered galaxy, which existed just 300 million years after the Big Bang, had already achieved 1/20th of the Sun's metallicity. That represents an astonishingly rapid pace of chemical evolution. Computer simulations of early galaxy formation predict much lower metallicities at this epoch. The models typically show metallicities that are around 1,000th to 1/10,000th of the solar value for galaxies at a redshift of 14. This galaxy exceeds those predictions by a full order of magnitude. The discrepancy points to a fundamental and incomplete understanding of the processes of early star formation and chemical enrichment. The metallicity of a galaxy affects many of its properties beyond just its chemical composition. Gas that has a higher metal content is able to cool more efficiently. The metals provide additional pathways for energy to be radiated away. More efficient cooling allows gas clouds to fragment into smaller pieces, which in turn allows them to form smaller stars. This creates a positive feedback loop where chemical enrichment enables different types of star formation to occur. The early onset of metal enrichment may have actually accelerated the assembly of galaxies. Measuring the metallicity of a galaxy precisely requires detecting multiple emission lines from different elements. Ideally, astronomers want to measure lines from oxygen, nitrogen, carbon, neon, and sulfur. The ratios between these different elements can reveal details about which types of stars were responsible for producing the metals. Unfortunately, at such extreme distances, only the very brightest emission lines are detectable. For this galaxy, the strong emission from oxygen provides the primary indicator of its metallicity. Other elements remain undetected, but they are presumably present at proportional abundances. The high abundance of oxygen specifically indicates that the enrichment came from massive stars. Core collapse supernovae are known to produce oxygen in abundance. Type Ia supernovae, which arise from the explosions of white dwarf stars, contribute less oxygen but more iron peak elements. The strong oxygen signature in this galaxy suggests that core collapse supernovae were the dominant source of enrichment. This aligns with our expectations that massive stars, which are the ones that explode as core collapse events, dominated the early stellar populations. It would be revealing to measure any spatial variations in the metallicity, but this cannot be done at such a great distance. The galaxy appears as an unresolved point source, smaller than a single pixel in the images. We cannot distinguish between a chemically uniform system and one that has enriched central regions and more pristine outer zones. Such gradients would be an indication of ongoing enrichment, with newly formed stars mixing with older, more metal-poor gas. Future observations with better spatial resolution might be able to reveal these details. The high metallicity creates a kind of chicken and egg problem. A high metallicity should make star formation more efficient, allowing more stars to form and further increasing the metallicity. However, reaching a high metallicity in the first place requires a substantial amount of prior star formation. The galaxy appears to be caught in a mature state, despite existing in the infant universe. It simultaneously shows the properties of youth through its small size and the properties of age through its chemical composition. Comparing this object to other high redshift galaxies will help to establish whether it represents an outlier or a typical example of its time. If many galaxies at similar distances also show an elevated metallicity, then our models will require a systematic revision. If this object is unique, then perhaps some special circumstances in its local environment enabled an unusually rapid rate of enrichment. The current statistics are insufficient to distinguish between these two scenarios. More observations are needed. The metal content whispers of hidden generations of stars. The very first stars that formed in the universe were radically different from those that are shining today. They contained absolutely zero metals, as they were formed purely from the hydrogen and helium that was created in the Big Bang. Astronomers refer to these hypothetical objects as population 3 stars. None of them have ever been observed directly, but our theories demand that they must have existed. This distant galaxy may preserve the chemical evidence of their legacy. Population 3 stars were likely enormous. Without any metals to facilitate cooling, the collapsing gas clouds that formed them could not fragment efficiently into smaller pieces. Larger clumps of gas stayed together, which resulted in the formation of more massive stars. Theoretical models suggest that their typical masses were between 30 and 300 times that of our own Sunday. Some of them may have even reached 1,000 times that benchmark, though such extremes remain speculative. These giants would have burned with an extraordinary brightness and heat. Their surface temperatures might have exceeded 100,000 degrees, making them glow with a brilliant blue-white light. They would have emitted copious amounts of ultraviolet radiation, ionizing the surrounding gas for dozens of light years in every direction. A single population 3 star would have shone as brightly as an entire modern galaxy filled with typical stars. They would have been impossible to ignore, but their lives would have been incredibly brief. Massive stars burn through their hydrogen fuel with incredible speed. While a typical star like our Sun might shine for 10 billion years, these giants would have exhausted their cores in just 2 to 5 million years. After they finished burning their hydrogen, they would have progressed through helium burning, carbon burning, oxygen burning, and silicon burning in rapid succession. Each of these stages would have lasted for a progressively shorter period of time, with the final stages taking mere days or even hours. Their deaths would have been nothing short of spectacular. Most of them would have exploded as pair instability supernovae, which completely disrupt the star, leaving no remnant behind. The energy of these explosions would have exceeded that of typical supernovae by factors of 10 or more. The blast would have enriched the surrounding gas with the full range of elements that were forged during the star's life, from carbon all the way up to iron and beyond. These explosions would have seeded their host galaxies with the very first metals. Some population 3 stars may have collapsed directly into black holes without exploding. If a star exceeds a certain mass threshold, its core collapse can produce a black hole that swallows the entire star before a shockwave has a chance to develop. These direct collapse events would have created black holes of perhaps dozens to hundreds of solar masses almost instantaneously. No chemical enrichment would have occurred from these events, but the black holes would have persisted and potentially grown through accretion and mergers. The evidence for population 3 stars remains indirect. We have never seen one directly. They existed too early in cosmic history and at too great a distance for our current instruments to be able to resolve individual stars. Instead, we infer their existence from the chemical patterns that we see in later generations of stars. The oldest stars that we can observe in nearby dwarf galaxies show chemical enhancement patterns that are consistent with enrichment by pair instability supernovae, which suggests that they had population 3 progenitors. This distant galaxy may have contained population 3 stars during its very earliest phases. If star formation began at 200 million years after the Big Bang, and this snapshot of the galaxy is from 290 million years, then any population 3 stars that formed initially would have already died. Their explosions would have enriched the gas from which the second and third generation stars then formed. The observed abundance of oxygen represents the cumulative output of these early stellar generations. Alternative scenarios do exist. Perhaps extremely massive black holes formed very early on through the direct collapse of gas clouds, without forming stars first. These black holes might have accreted matter rapidly growing to supermassive sizes within just a few 100 million years. Their accretion disks would have emitted intense radiation which could have possibly photo-evaporated the surrounding gas and suppressed any further star formation. Such processes might have accelerated the apparent evolution of galaxies. The question of population 3 stars remains one of the most fundamental unsolved problems in the field of astrophysics. When did they form? How massive were they typically? How did they die? And how efficiently did they enrich their environments? Each one of these answers constrains our understanding of cosmic evolution. This galaxy, which exists in the very epoch when population 3 stars should have just finished their work, offers a crucial laboratory for testing our theories. Its properties must somehow be connected to the nature of those mysterious first stars. The unseen first generation of stars casts long shadows across time. Galaxies should not be able to assemble themselves this quickly. Our current theory describes a hierarchical process where small structures form first and then gradually merge together to build larger systems over billions of years. This bottom-up assembly process takes a significant amount of time. Small dark matter halos form first accreting gas and forming the first stars. These small galaxies then collide and merge with one another, building up progressively larger galaxies. This process should be ongoing throughout the entire history of the cosmos. This distant galaxy appears to have skipped several steps in this process. It shows the properties of a mature system, despite existing at a time when the universe had barely begun the process of structure formation. Its size, its mass, and its metallicity all suggest a system that has undergone a substantial amount of evolution. Yet the timeline only allows for a brief window for that evolution to occur. Something about the conditions in the early universe must have enabled a dramatically accelerated rate of assembly. Dark matter plays a central role in the process of structure formation. This invisible substance outweighs normal matter by a factor of 5 to 1. Its gravity is what pulls gas into dense concentrations where star formation can occur. Understanding the properties and distribution of dark matter at early times is essential for explaining the galaxies that we observe. Our current observations suggest that there was something unexpected about how dark matter behaved in the infant universe. The standard cold dark matter model assumes that dark matter particles are massive, slow-moving, and collisionless. They interact with other matter only through the force of gravity. This simplicity allows for very precise predictions for how structure should form. Density fluctuations grow through gravitational instability in a well-understood manner. Small halos form first when the fluctuations reach a sufficient amplitude. Larger halos then assemble later on through the process of mergers. The timeline for this process depends on the amplitude of the fluctuations that were measured in the cosmic microwave background. Extrapolating forward from the measurements of the cosmic microwave background, our models predict that dark matter halos massive enough to host bright galaxies should be extremely rare at this early epoch. At a redshift of 14, the probability of finding even a single such halo in a survey covering the area observed by the James Webb Telescope is very small, yet multiple candidates have been found. Either the observations are systematically biased in some way, or the models are underpredicting the abundance of high redshift halos. Modified properties of dark matter offer potential solutions to this problem. If dark matter is warmer than we have assumed, consisting of lighter, faster-moving particles, then the formation of small-scale structures would be suppressed, while large-scale structures would form normally. This could affect the merger rate and the assembly history of galaxies. However, the concept of warm dark matter conflicts with observations of the smallest dark matter halos that have been detected through gravitational lensing. The constraints on this model are very tight. Alternatively, if dark matter particles are able to interact with each other through forces other than gravity, the internal structure of the halos would change. Self-interacting dark matter would create halos with more uniform density profiles, rather than the cuspy profiles that are predicted for collisionless dark matter. This would affect how the baryons or normal matter behave within the halos, potentially changing the processes of gas cooling and star formation. The magnitude of the self-interaction required to significantly affect early galaxy formation would need to be carefully chosen to avoid conflicting with observations of galaxy clusters. Another possibility involves primordial black holes as a component of dark matter. If some fraction of the dark matter consists of black holes that were formed in the very early universe, they would have seeded the formation of galaxies differently than particle dark matter. Black holes can accrete the surrounding gas, growing in size and creating feedback that affects star formation. A population of seed black holes might have accelerated the formation of the first galaxies. However, constraints from gravitational wave observations and microlensing surveys limit how much of the dark matter can be in the form of primordial black holes. The standard cold dark matter model may simply need to be refined rather than completely replaced. Perhaps the transfer function that relates the early fluctuations to the later structures has some uncertainties at the small scales that are relevant for early dwarf galaxies. Perhaps the initial fluctuation spectrum has some features that are not captured by our simple power law approximations. Small modifications like these might be able to reconcile the observations with the theory without abandoning the successful framework of the model. Baryonic physics could also be responsible for the discrepancy rather than the properties of dark matter. If gas cooling and star formation were far more efficient at high redshift than we currently model, then even standard dark matter halos could produce bright galaxies. The feedback prescriptions that are used in our simulations, which regulate how supernovae and stellar radiation affect the surrounding gas, may not be correctly capturing the physics in the extreme environments of the early universe. Getting the feedback right is a notoriously difficult problem, and it remains a major uncertainty in our models of galaxy formation. Observations at slightly lower redshifts can provide additional constraints on these theories. If the early formation of galaxies is due to modified dark matter, then the effects should persist and be visible at redshifts of 5 to 10 as well. If the effects are specific to the highest redshifts, then environmental differences or evolutionary processes that are unique to the earliest times are more likely to be responsible than the fundamental physics of dark matter. Comparing galaxy populations across different redshifts will help to isolate the causes. Future observations will be able to test these dark matter scenarios directly. Gravitational lensing of distant galaxies by foreground dark matter halos allows for the measurement of the masses and density profiles of the halos. Comparing these lensing measurements at various redshifts can constrain how the properties of dark matter halos evolve over time. Any discrepancies between the predicted and observed evolution would point toward new physics. These tests will require large samples and very high precision measurements, but they are achievable with upcoming facilities. The abundance of satellite galaxies around larger systems also provides a test of dark matter models. Cold dark matter predicts that there should be more small satellites than are observed locally, which is the famous missing satellites problem. Perhaps many of these satellites do exist, but they fail to form stars, and so they remain dark. Or perhaps the physics of dark matter prevents their formation in the first place. Observing satellite populations at high redshift before environmental effects have had a chance to strip the gas from the small halos may be able to resolve this long-standing tension. Dark matter governs the scaffolding upon which the visible structures of the universe are built. Any unexpected behavior in that scaffolding will create visible consequences. The early galaxies that are now being discovered represent consequences that we did not anticipate. Whether the cause of these consequences lies in the nature of dark matter itself or in how the baryons respond to that dark matter remains uncertain. Disentangling these possibilities will require more data, better models, and a great deal of creative thinking. The invisible foundation of the cosmos is cracking under our scrutiny. The universe's schedule appears to be far more compressed than we ever imagined. Galaxies assemble through a complex interplay of processes involving gravity, gas dynamics, star formation, and feedback. Each of these processes has a characteristic timescale that is imposed by the laws of physics. Gravity acts quickly collapsing structures on free fall times. Gas dynamics involves pressure, cooling, and turbulence, all of which slow down the process of collapse. Star formation converts gas into stars over timescales of millions of years. Feedback from those stars then affects the surrounding gas, regulating any future formation of stars. Coordinating all of these different processes should take a significant amount of time. The observed galaxies suggest that this coordination happened with remarkable speed. Consider the sequence of steps that is required. First, the density fluctuations in the dark matter must grow to a nonlinear amplitude where the halos can virialize. Virialization means that the collapsing structure has reached a state of dynamical equilibrium, with its motions randomized and its potential energy converted into kinetic energy. This is what sets the gravitational potential well within which gas can begin to accumulate. The timescale for virialization depends on the mass of the halo and its initial overdensity. Second, the baryonic gas must fall into this dark matter potential well. The gas starts at the mean cosmic density and must flow inward. This infall is hindered by pressure resistance. As the gas is compressed, it heats up. This heated gas must then radiate away its energy in order to continue collapsing. Radiative cooling proceeds through atomic transitions with rates that depend on the gas density, temperature, and composition. In the primordial universe, with no metals present, cooling via atomic hydrogen lines is a relatively inefficient process. Third, the cooled gas must reach the densities where star formation can occur. This requires the gas clouds to become self-gravitating and unstable to further collapse. Turbulence, magnetic fields, and thermal pressure all work to resist this collapse. The gene's mass is what sets the scale at which gravity is able to overcome pressure. Only clouds that exceed the gene's mass can collapse to form stars. Building up a sufficient mass of gas in a concentrated region takes time, as more and more gas continues to rain down from the surrounding halo. Fourth, the process of star formation itself proceeds through a complex series of physical events, including the fragmentation of molecular clouds, the formation of protostellar cores, the accretion of matter onto these protostars, and eventual ignition of nuclear fusion. This entire sequence requires multiple different timescales. The freefall time gives the minimum duration for a cloud to collapse. The accretion timescales determine how quickly the protostars are able to gain mass. The Kelvin-Helmholtz time governs how long a protostar takes to contract down to the main sequence. Summing up all of these contributions yields timescales of hundreds of thousands to millions of years for each stellar generation. Fifth, the feedback from the stars has an impact on the surrounding medium. The radiation from massive stars heats and ionizes the nearby gas. Stellar winds blow material outward. Supernovae inject enormous amounts of energy, driving shock waves and potentially expelling gas entirely from the halo. The timescale for this feedback to have an impact on the system depends on how quickly the supernovae occur and how far their energy is able to propagate. In small halos, the feedback acts quickly because the scales are so compact. The entire system can be affected within just a few million years. Sixth, this entire cycle must repeat for multiple generations in order to build up the observed level of chemical enrichment. After the first generation of stars dies and disperses its metals, the enriched gas must then cool again and form new stars. Each one of these cycles adds several million years to the total timeline. It seems that 3 to 10 such cycles are necessary to reach the observed metallicity levels, which implies a total duration of tens to hundreds of millions of years. Remarkably, all of these steps were apparently completed within just 1 to 200 million years for the galaxies that have been observed at a redshift of 14. This suggests that the processes must have overlapped in time rather than occurring in a strictly sequential manner. Perhaps star formation began before all of the gas had even finished falling into the halo. Perhaps multiple different regions within a single protogalaxy were at different evolutionary stages at the same time. Perhaps the feedback, rather than shutting down star formation entirely, actually sculpted the gas flows in ways that sustained the formation of stars. A kind of parallel processing across a spatially extended system could have compressed the timelines. If a protogalaxy that spans thousands of light years contains multiple semi-independent star-forming regions, each of those regions can evolve on its own timeline. When viewed as an integrated whole, the system would appear to be more evolved than any single region, because the different regions would be contributing stars that were formed at different times. The overlap would create the illusion of rapid evolution when the actual pace per region was more reasonable. However, even when accounting for this spatial overlap, the timelines remain incredibly tight. The laws of physics impose lower limits on these processes that cannot be eliminated through clever accounting. Gas cooling cannot happen faster than the radiative processes will allow. Stars cannot evolve faster than the rates of nuclear fusion will permit. Supernovae cannot disperse their material faster than the velocity of the ejector. Each one of these limits is firm. Making galaxy formation work within the observed timescales requires pushing every single process to near its physical limit all at the same time. This seems unlikely to happen just by chance. It is more probable that there is some process or mechanism that was operating at these early times that is not included in our current models. Perhaps the dark matter halos at high redshift were able to accrete gas far more rapidly than is predicted. Perhaps the radiation background from the very first stars affected the process of gas cooling in ways that enhanced rather than suppressed star formation. Perhaps magnetic fields, which are largely ignored in our current simulations due to their computational cost, played important roles in channeling the gas and regulating its collapse. Identifying this missing piece of physics is the next great challenge. The universe accomplished in just hundreds of millions of years what our models say should have required billions. The reionization of the universe marks a major phase transition in its history. The neutral hydrogen that dominated the early universe was gradually ionized by the radiation from the first stars and galaxies. This process transformed the intergalactic medium from being opaque to being transparent over the course of several hundred million years. The exact timing and nature of this reionization process remain incompletely understood. Early galaxies like the record-breaking system that was discovered provide critical clues about this important epoch. Reionization required an enormous amount of ionizing radiation. Every single hydrogen atom in the universe needed to absorb an ultraviolet photon that was energetic enough to strip away its electron. This happens at wavelengths that are below 91 nanometers. Only very hot stars are capable of producing a sufficient flux of ultraviolet light in this range. The most massive stars with surface temperatures that exceed 30,000 degrees are prolific emitters in the far ultraviolet. Early galaxies that were dominated by these massive stars would have been prodigious sources of ionizing radiation. The observed properties of this distant galaxy suggest that it was producing ultraviolet radiation very efficiently. The high rates of star formation that are inferred from its emission lines mean that many massive stars were forming continuously. These stars would have lived for only a brief time and died as supernovae. But while they were alive, they would have blazed with intense ultraviolet light. A significant fraction of that light would have escaped the galaxy and gone on to ionize the surrounding intergalactic gas. The escape fraction of this ionizing radiation is what determines how effectively galaxies are able to contribute to the process of reionization. Measuring these escape fractions directly at high redshift is a very challenging task. The ionizing photons get absorbed by the neutral hydrogen in the intergalactic medium long before they can reach our telescopes. We are only able to detect the light at longer wavelengths that is not absorbed. Indirect methods involve measuring the non-ionizing ultraviolet flux and then modeling the stellar populations to estimate how much ionizing flux should have been produced. These models depend on our assumptions about the temperatures, atmospheres, and mass distributions of the stars. The chemical composition of a galaxy also has an effect on its ionizing output. The metals in the atmospheres of the stars can absorb some of the ultraviolet light before it is able to escape the star. Metal-poor stars therefore emit more ionizing photons than metal-rich stars of the same mass. The relatively high metallicity of the observed galaxy suggests that its stars contained enough metals to slightly suppress their ionizing output compared to truly pristine population 3 stars. However, the stellar population was likely still more metal-poor than typical modern stars, which would have allowed it to maintain a high ionizing efficiency. The galaxy's contribution to the process of reionization depends on both its rate of ionizing photon production and its number density. If similar galaxies were common at this early epoch, then collectively they could have provided a significant amount of ionizing flux. If this galaxy represents a rare and unusual object, then its individual contribution would have been minor. Our current estimates suggest that the galaxies that are being observed by the James Webb Telescope at high redshift are numerous enough to have driven the process of reionization, but the uncertainties in these estimates remain large. Reionization proceeded in an inhomogeneous manner. The dense regions of the universe that contained more galaxies would have been ionized first, creating ionized bubbles that then expanded outward. The lower density voids between the galaxies would have remained neutral for a longer period of time. Eventually, these ionized bubbles would have overlapped, completing the process of reionization for the entire universe. The topology of this process, including the size distribution of the ionized regions and the timing of their overlap, all depend on the spatial distribution of the early galaxies. Observations of distant quasars can provide information about the progress of reionization. The light from a quasar that passes through the intergalactic medium shows absorption features from any neutral hydrogen that is along the line of sight. The amount of this absorption indicates the ionization state of the medium. These measurements show that the universe was substantially ionized by a redshift of 6, with the process of reionization being largely complete by that time. Earlier than that, the ionization fractions decrease, which indicates that reionization was still ongoing. The discovered galaxy at a redshift of 14 existed during the very early phases of reionization. The intergalactic medium around it would have contained a mixture of both ionized and neutral regions. The galaxy itself would have sat within an ionized bubble that was created by its own radiation and that of any neighboring galaxies. The size of this bubble would have depended on how long the galaxy had been producing ionizing photons and how quickly those photons were able to propagate into the surrounding neutral gas. Simulations of reionization attempt to track the growth and overlap of these ionized bubbles. These simulations require knowing the galaxy population at each redshift, including their number density, their spatial clustering, and their ionizing output. The observations of real high redshift galaxies provide critical input for these simulations. Each new discovery helps to refine the models. The cumulative effect of many such observations will be a realistic simulation of how the process of reionization actually unfolded. The relationship between galaxies and reionization is a bidirectional one. Galaxies caused reionization by producing ionizing radiation, but reionization also had an effect on the galaxies. Ionized gas has a higher pressure than neutral gas, which makes it harder for it to collapse into low-mass halos. Reionization may have therefore suppressed the formation of small galaxies, setting a minimum mass scale for galaxy formation. This process of photoevaporation would be visible as a change in the galaxy mass function before and after reionization. Understanding reionization is important for interpreting observations at all cosmic epochs. The ionization state of the intergalactic medium affects the transmission of light from distant objects. It influences the temperature and pressure of the gas that eventually falls into galaxies. It determines the radiative environment in which the early galaxies evolved. Reionization was a watershed moment in the history of the cosmos, separating the Dark Ages from the Age of Galaxies. Pinpointing exactly when and how this transition happened remains a frontier question in astronomy. The early galaxies hold the answers. The cosmic fog was lifted by their collective light. The process of finding and characterizing this distant galaxy required an extraordinary observational effort. Over 200 hours of time on the James Webb Space Telescope were dedicated to this single, small patch of the sky. In an era when telescope time is among the most valuable and scarce resources in the field of astronomy, this investment represents a major commitment. The scientific return has more than justified the cost. The observations occurred in multiple different phases, using different instruments on the telescope. The near-infrared camera provided the initial imaging across multiple different wavelength bands. Each of these bands required separate exposures in order to build up a sufficient amount of signal. Longer exposures help to reduce the amount of random noise, which allows for fainter objects to be detected. For the very deepest bands, the integration times exceeded 30 hours per filter. The telescope had to stare at the same region of the sky for hours on end, slowly and patiently accumulating photons. Scheduling these observations required a great deal of careful planning. The James Webb Telescope orbits the second Lagrange point, which is 1,000,000 miles away from the Earth. Its field of view can only be pointed at certain parts of the sky at certain times of the year. The target region needed to be observable during the scheduled observation windows. The weather on Earth does not have any effect on space telescopes, but instrumental scheduling limitations on data storage and competing observation requests all serve to constrain what can be done and when. The observations with the mid-infrared instrument added another layer of complexity to the project. MIRI requires even longer integration times than NIRCam due to its lower sensitivity. The infrared backgrounds from the telescope's own thermal emission must be carefully subtracted from the data. The observations had to alternate between pointings that were on the source and pointings that were offset in order to measure this background. This calibration process consumed additional time beyond the pure science integration time. The process of data reduction transformed the raw detector frames into science-ready images. Each frame contains instrumental signatures that must be removed. Hot pixels, cosmic ray hits, electronic noise, and flat field variations all appear in the raw data. The pipeline software corrects for these effects using calibration files that are derived from both laboratory measurements and on-orbit characterizations. The process is largely automated, but it still requires human oversight to catch any anomalies. Combining multiple different exposures into the final images requires a very precise alignment between the exposures. The pointing of the telescope can drift slightly due to thermal variations and micro-vibrations. The images must be registered to a sub-pixel accuracy before they can be co-added. The software identifies stars or other point sources that appear in multiple frames and then calculates the offset between the frames. After shifting the frames to a common reference, they can be averaged together, which increases the signal-to-noise ratio. The spectroscopic follow-up demanded additional time on the telescope. The near-spec instrument is able to observe dozens of objects simultaneously using a programmable micro-shutter array. Small metal shutters can be opened or closed to create custom slit patterns. Configuring the shutters for this particular galaxy required knowing its precise position from the images. The spectrum was built up through many individual exposures, each one of which lasted for thousands of seconds. Different gratings were used to provide coverage at different wavelengths. The ALMA observations from the ground served to complement the space-based observations. Arranging for time on ALMA is also a highly competitive process. Proposals are reviewed and ranked, and only the highest priority science receives any time. The ALMA observations required excellent atmospheric conditions, which are only achieved a fraction of the time at the high-altitude site. When the conditions were right, the array was pointed at the target for hours, letting the rotation of the Earth provide different baselines and build up coverage in the Fourier plane. The data from the multiple different telescopes and instruments then had to be combined very carefully. Each dataset has its own different calibration uncertainties and systematic effects. Merging them together requires a thorough understanding of these systematics and the proper weighting of the data. When different measurements agree, our confidence in the results increases. When they disagree, troubleshooting is required to identify which measurement is problematic. The human effort that went into these observations should not be overlooked. Dozens of astronomers contributed to the planning, execution, reduction, and analysis of the data. Each one of them brought their own specialized expertise to the project. Some of them designed the optimal observation strategies, others developed the algorithms for data reduction. Still others were responsible for interpreting the scientific results. The collaboration between different institutions and countries is what made this work possible. No single person could have accomplished this alone. Publishing the results required a great deal of careful documentation. Scientific papers must describe the methods in sufficient detail that other researchers can evaluate the conclusions. The supplementary materials for this discovery include hundreds of pages of technical details. Peer reviewers scrutinized every single claim before the paper was published. This process ensures the quality of the research, but it can take months or even years from the initial submission to the final publication. The observational investment will continue to pay dividends for many years to come. The deep images and spectra can be reanalyzed to study other objects that are in the same field of view. Fainter galaxies that were previously below the detection thresholds might emerge from the noise with improved analysis techniques. Serendipitous discoveries often emerge from data that was taken for different purposes. The dataset is a resource that is available to the entire astronomical community. 200 hours of staring into the darkness have revealed a new and unexpected light. This discovery is just the beginning of a new chapter in astronomy. Finding a single galaxy with such extreme properties immediately raises the question of whether others like it exist. Are such objects common or are they rare? Answering this question will require observing many more fields in order to detect additional examples. Multiple future observations are already planned to address this very question. The James Webb Telescope will continue to survey high redshift galaxies as part of its ongoing mission. The JADES program has multiple observation cycles that have been approved, which will cover additional areas of the sky to varying depths. Each new field provides new opportunities to find similar objects. By observing many different fields, astronomers will be able to build up statistics on the abundance of bright, chemically evolved galaxies at various redshifts. patterns only begin to emerge with sufficient sample sizes. Other deep surveys that are using the James Webb Telescope are targeting different regions of the sky and using different strategies. Some of these surveys are focusing on wider areas with shallower exposures, which is an efficient way of finding the brightest objects. Others are drilling extremely deep into very small regions, pushing the telescope to its faintest possible limits. The combination of both wide and deep surveys will allow us to sample different populations of galaxies. Wide surveys are good at finding the typical objects. Deep surveys are good at finding the rare objects. Both are necessary for a complete understanding of the early universe. Ground-based telescopes will continue to play important roles in this research. ALMA is currently conducting systematic surveys of high redshift galaxies to measure their molecular gas content. These observations will complement the information on the stellar populations that is coming from the James Webb Telescope. Together they will constrain both the properties of the stars and the gas, which will provide a complete picture of the properties of these galaxies. ALMA's large collecting area and its excellent sensitivity make it the ideal instrument for these kinds of spectroscopic surveys. Future extremely large telescopes will provide even better capabilities. The Giant Magellan Telescope, the 30-meter telescope, and the Extremely Large Telescope, all of which are currently under construction, will be the largest optical telescopes ever built. Their mirror diameters will exceed 25 meters, which will provide a collecting area that is more than 10 times that of the current large telescopes. This will enable the spectroscopy of even fainter objects, as well as higher resolution imaging that will be able to resolve their internal structures. Space-based missions that will go beyond the James Webb Telescope are also under development. The Nancy Grace Roman Space Telescope, which is scheduled for launch in the late 2022, will conduct wide-field surveys that will cover areas that are 100 times larger than Webb can efficiently observe. Roman will find thousands of high redshift galaxies, which will help to identify the most interesting targets for detailed follow-up observations with other facilities. Its panoramic view will complement Webb's deep focus. Further, in the future, mission concepts exist for telescopes that will be even more powerful than James Webb. The Habitable Worlds Observatory aims to directly image and characterize Earth-like planets around nearby stars, but it will also have the capabilities to study distant galaxies. LUVOI, the Large Ultraviolet Optical Infrared Surveyor concept, would dwarf the James Webb Telescope in both size and sensitivity. These missions are still decades away from being launched, but they represent the long-term future of space astronomy. Radio astronomy is also continuing to advance with the construction of new facilities. The Square Kilometre Array, which is currently under construction in Australia and South Africa, will be the most sensitive radio telescope ever built. Its large collecting area will enable the detection of faint emission from high redshift galaxies, which will allow us to measure their gas properties and their kinematics. The NGVLA, or Next Generation Very Large Array, which has been proposed for construction in the United States, would provide similar capabilities but with a higher resolution. Coordinated multi-wavelength observations are what will allow us to extract the maximum amount of science from each target. When a new high redshift galaxy is discovered in infrared images, follow-up observations at radio submillimeter and optical wavelengths will help to build a complete dataset. Each wavelength probes different physical properties, combining the information from across the entire electromagnetic spectrum will allow us to constrain our models far better than any single wavelength ever could. International collaborations will ensure that the appropriate facilities are applied to the most interesting targets. Machine learning techniques are being developed to help identify high redshift galaxy candidates automatically in these large datasets. Humans can visually inspect hundreds of images, looking for faint red objects. Computers can inspect millions. Training algorithms on known high redshift galaxies allows them to recognize similar objects in new data. This automated candidate selection process will help to accelerate the pace of discovery. Although spectroscopic follow-up is still required to confirm the redshifts, citizen science projects are engaging the public in the process of galaxy classification and discovery. Platforms like Galaxy Zoo allow volunteers to examine astronomical images and classify the objects that they see. Occasionally, these volunteers discover unusual objects that professional astronomers have missed. The collective effort of thousands of volunteers can help to process datasets that are too large for small research teams. This democratization of discovery benefits both science and education. Theoretical predictions can help to guide us on where to look for interesting objects. Simulations of galaxy formation can help to identify the regions of parameter space where extreme objects might exist. If the models predict that the brightest high redshift galaxies preferentially form in overdense regions, then surveys that are targeting known overdensities will be the most efficient. Combining theory and observation is what helps to optimize the usage of our telescope time. The sample size of these early galaxies will continue to grow over the coming decade. Dozens of similar objects may be found, and eventually hundreds. At that point, the statistical characterization of the early galaxy populations will become robust. Individual objects will transition from being curiosities to being representatives of an entire population. The questions will shift from, does this exist, to how common is this, and what causes the observed distribution of properties. The field will mature from an era of discovery to an era of understanding. The search for our origins is expanding across the entire sky. Chemistry is what enables complexity. Without the existence of heavy elements, no planets could ever form. Without oxygen, no water could ever exist. Without carbon, no organic molecules could ever emerge. The rapid rate of chemical enrichment that has been revealed by this distant galaxy has profound implications for when and where the building blocks of life first appeared in the universe. The story of chemistry is the story of possibility. In the primordial universe, only hydrogen, helium, and a trace amount of lithium existed. These three simple elements alone cannot be used to build complex structures. No solid surfaces can be formed from them. No long-chain molecules can exist. No self-replicating systems can emerge. Life requires a much more diverse kind of chemistry. That diversity comes from the process of stellar nucleosynthesis, which is the fusion of light elements into heavy ones inside the cores of stars. Every single carbon atom that is in your body, every oxygen molecule that you breathe, every calcium atom that is in your bones was forged in a star billions of years ago. The timeline for this process of chemical enrichment is what determines when the prerequisites for life could first be met. If enrichment takes billions of years to occur, then the earliest epochs of the universe would have remained chemically hostile to life. If enrichment proceeds rapidly, then the potential for complex chemistry and eventually life could have arrived very early on. The discovered galaxy proves that this process of enrichment began almost immediately in cosmic terms. Within just 300 million years, a significant amount of oxygen already existed. It is probable that carbon, nitrogen, and other bioessential elements also existed as well. This does not mean that life actually arose at a redshift of 14. The chemical preconditions are a necessary but not a sufficient condition for life. Planets must first form from this enriched material. Those planets then need to have stable environments that would allow for the existence of liquid water. Organic chemistry must then be able to produce increasingly complex molecules, and eventually self-replication must emerge. Each one of these steps requires additional conditions beyond the mere availability of the right elements. The pathway from chemistry to biology is a long and uncertain one. However, the early appearance of these heavy elements opens up much wider windows of opportunity. If galaxies at a redshift of 14 contained a sufficient amount of oxygen to form water and a sufficient amount of carbon to build organic molecules, then the clock for biological evolution could have started surprisingly early. In principle, any planets that formed from the gas that was enriched by these early galaxies might have had billions of years for life to develop, long before the Earth even formed. Such ancient biospheres could exist on planets that are orbiting stars that were born in the first billion years of cosmic history. The distribution of the elements matters just as much as their total abundance. If the early enrichment was highly localized with the oxygen concentrated in small regions, while most of space remained pristine, then planet formation would have only been able to succeed in these favored locations. If the enrichment was widespread, then the opportunities for chemistry would have existed broadly. The efficiency with which the enriched ejecta from supernovae was mixed throughout the galaxies is what determines how uniformly the heavy elements were distributed. The supernovae in the early universe exploded into environments that were much denser than those of later supernovae. The intergalactic medium was much more compact. The ejecta from a single supernova could travel less far before it encountered a significant amount of gas. This would have favored an efficient mixing on galactic scales, but it might have limited the enrichment of the broader intergalactic medium. The voids between the galaxies probably remained more pristine for a longer period of time than the regions within the galaxies. The first generation of planets that formed from this slightly enriched material would have contained more heavy elements than the population, 3 stars but far less than the Earth. Such low metallicity planets would have been different from the modern rocky planets that we are familiar with. They might have contained relatively more carbon compared to oxygen, which would have produced carbide minerals rather than silicates. Their atmospheres might have been dominated by hydrogen, making them resemble small versions of gas giants. Whether such planets could have ever harbored life remains a speculative but intriguing question. Finding planets around metal-poor stars provides us with tests of our theories of early planet formation. Recent surveys have detected a few planets that are orbiting stars with metallicities that are below 10% of the typical values. These discoveries prove that planet formation can occur with a limited amount of heavy elements. The minimum metallicity that is required for planet formation remains an uncertain quantity. Perhaps even the first-generation stars with metallicities that were below 1% could have formed some planets. Each new discovery of such a planet pushes this limit lower. The presence of water elsewhere in the universe is dependent on the abundance of oxygen. Water molecules require oxygen atoms to be able to bond with hydrogen. The high oxygen content of the discovered galaxy guarantees that water could have formed in or around it. Clouds of water vapor might have existed in the galaxy's interstellar medium. Icy planetesimals might have condensed in the protostellar disks. The ingredients for water emerged surprisingly early in the universe. Life as we understand it requires liquid water, but many different chemicals participate in the processes of biology. Amino acids, the building blocks of proteins, contain carbon, nitrogen, oxygen, and hydrogen. Nucleic acids, which form DNA and RNA, additionally require the element phosphorus. Lipids, which form the cell membranes, consist of chains of carbon and hydrogen. Each one of these elements becomes available through the process of stellar nucleosynthesis at different rates. Achieving the full suite of bioessential elements requires an extensive amount of enrichment. The implications of this discovery extend beyond just the possibility of life to its potential inevitability. If chemical enrichment proceeded rapidly everywhere in the universe, then the cosmos would have quickly become filled with the raw materials for complexity. Billions of galaxies, each of them containing billions of stars, each of them potentially hosting planets with the right chemistry. The sheer number of potential sites makes the existence of life elsewhere in the universe seem almost certain. The question then shifts from could life exist elsewhere to how common is it and where should we be looking for it? Searching for biosignatures in the atmospheres of exoplanets represents one approach to finding life beyond the Earth. Upcoming telescopes will be able to analyze the atmospheric composition of potentially habitable planets. Detecting oxygen, methane, and other gases in combinations that would suggest biological activity would provide strong evidence for life. However, the possibility of false positives from non-biological processes will always remain. Confirming the existence of life will require multiple independent lines of evidence. The chemical history of the universe unfolds as a story of increasing complexity, from simple hydrogen and helium to the full periodic table, from primordial clouds to stars and planets, from minerals to molecules, from chemistry to biology, from simple organisms to intelligence. Each one of these steps builds on the ones that came before it. The rapid chemical enrichment of the early universe served to accelerate this progression. The timeline from the Big Bang to complex chemistry was compressed into just hundreds of millions of years instead of billions. The discovered galaxy represents a major milestone in that progression. It marks the era when the chemistry of the universe diversified, when the possibilities expanded beyond just simple hydrogen and helium. The oxygen in its spectrum signals the end of chemical simplicity and the beginning of elemental richness. That transition is what made everything that followed it possible. Stars like our Sun, planets like our Earth, and life like our own. The chain of consequence connects that ancient galaxy directly to us. We are made of the ashes of those very first stellar generations. Their explosions enriched the gas that eventually became our own solar system. Their chemistry is our chemistry. The universe learned how to make the elements very quickly, and then it had billions of years to explore what those elements could become.